Hey guys! Today we're diving into the world of digital electronics, focusing on basic components like logic gates. Logic gates are the building blocks of digital circuits, performing fundamental operations on binary inputs. Here you can see some logic gates. These are the symbols that represent them. We have AND, NOT, OR, NOR, etc. The AND gate outputs true only if both inputs are true. We're going to work with two inputs, A and B. We're going to look at those truth tables, mainly AND, OR, and XOR. So, AND's truth table shows that only when both A and B are 1, the output is 1. The OR gate outputs true if at least one input is true. So if either A or B is 1, the output will be 1. The XOR gate outputs true only if the inputs are different. So if A and B are 1 and 0, or 0 and 1, the output is 1. Let's take a quick look at the truth tables for these gates to solidify our understanding. So I said that AND gate shows that only when both A and B are 1, the output is 1. Here you can see that only in this case we get a 1. The OR gate outputs true if at least one input is true. So we can see here that we have 1, 0, the output is 1, 0, 1, the output is 1, and 1 and 1, the output is 1. The XOR gate outputs true if only the inputs are different. So we get 1 and 1 only in these two rows. And on the other ones, we get 0. Let me introduce you to the Hall adder. We're going to build a circuit together. This is a Hall adder. It has two outputs, the sum and the carry. The sum is produced by the XOR gate, and the carry is produced by the AND gate. We're gonna just simply look at the full adder first, and then we're gonna draw both of them. This is the full adder, which can handle the addition of 3 inputs, 2 bits, and a carry in. So a half adder doesn't have the carry in. And we're going to understand when we need to use a half adder and when we need to use a full adder. The full adder actually contains of 2 half adders and an OR gate to produce the final sum and the carry out. So we need to draw this. Let's start. So let's first draw the half adder. So we have an input of an A and B. We're going to connect them with wires. This is the wire for A, and this is the wire for B. We're going to XOR them together. I'm going to draw now, and then we're going to check if some kind of calculator works right or not. So this is the XOR gate. We XOR the A and B together, which produces us the sum. Then we take the same A and the same B and AND them together to get the carry. This is the carry output, not the carry input. The half adder doesn't have a third input. That's why we need to use a full adder. So we AND them together and we get a carry. So for example, if we're adding 2 numbers, 1 plus 1, this gives us 10. So if we do it like this, we get a sum of a 0 and the carry of 1 here. If we had another number over here, it would add to that number, which means we'd have a carry in. So in this case, we didn't need a carry in, so we can use a half adder. But if we're adding, for example, this number to this, we have 1 plus 1, which is 0, carrying 1. So here we have a carry in, and the half adder just wouldn't work. So let's start by building the full adder. So as I said, The full adder combines two half adders and an OR gate to produce the final sum. And a carry out, of course. So we're gonna add the carry in here. This is the wire for carry in. We're gonna name it CIN. This is our carry in. We take the carry in and our sum here and XOR them. Which gives us the final sum. Then we take the carry in and the sum again, and we end them. So here you can clearly see that the carry in and the sum are basically our inputs A and B. So we end them together, and this produces a carry. Then we take our initial carry and OR them together. This is our carry out. Take C and write out. So this is a full adder. So if we have here a carry in, this can work. So if we try to add 11 plus 1, again, we have 0. Here we have 1, a carry. So let's just try to do this column first. So for example, this is our A, and this is our B. So we have 1 here, 1 here. If we XOR those two ones together, as we learned from the truth table, we will get a 0. Our carry in the first column is 0. So we'll write a 0 here. If we end 1 and 1 together, we're going to get a 1. So we have 1 here, we're getting 1. So here we have a carry of 1. Then we have a 0 here and a 0 here. If we XOR two zeros together, we're getting a 0. So the sum is 0. Then we have 0 here and 0 here. So the end will be 0 again. And if we OR these two together, the carry out will be 1. So here we have 1. This is our carry out. This is the sum. If we continue this addition, we'll have 1 plus 1, which is 0, and the carry here, 1. So this comes here as 100. So, which means we have another carry here. And if we try to do the same thing with the second column and denote this one to be A, and here we have a 0 to be B, and a carry of 1 here, we'll get the same results. So we'll get a carry of 1 and a sum of a 0. That wraps up our exploration of half adders, full adders, the logic gates. I hope this helped you understand the basics of how binary arithmetic works in digital circuits. These are foundational concepts used in building more complex systems like processors and calculators. If you found this video helpful, be sure to like, share, and subscribe for more content on digital logic and computer science. Feel free to drop any questions in the comments, and I'll see you in the next one.